In this lesson, we'll be studying the topic of, as you see here, it's u substitution. Now we're going to use u substitution here with finding the derivative of things, and we're going to look at functions that might look a little complicated but really simplify down to an easier function, and we're going to use substitution to do that. And we've used substitution in algebra before. In many different cases we use substitution. So it's the same idea. We're going to be applying it here to calculus, and we're going to be differentiating here. So we're going to find like dy in terms of dx and something like that. So as you look at these first five lines here, we have y equals e to the x squared plus 2. Well, what we can do is we can recognize that as really y equals e to some power, and we use u to represent an expression usually. So here we have this part right here, that's going to be our u. And so instead of putting y equals e to the x squared plus 2, we're going to put y equals e to the u, which is something easier to differentiate. Same thing with the rest of these. This next one is really something to the 100th power. It's x cubed minus 2x squared plus 1, but let's just say it's u to the 100th power. So that's what we see here. The next few are similar. This could represent our u, and we would substitute in, and it really looks like y equals natural log to the u. Same thing with this one. And the next one, this one is actually a cubed function. So we can think, okay, we might think, oh, I see a sine of x. That seems to be our basic function. And that's the word I'll use here is the basic function. So each of these first five broke down into some basic function. So the second one here looks pretty complicated, but the basic function is just something to 100th power. For the third one, it's just the basic function is natural log. And then down to the last one, this one we have to be careful with because we might think, oh, well, the basic function, it looks like it's sine x, but really it's something cubed, so we can let that sine x equal u, and so it's something cubed. Also, remember, we'll see this in the form sine cubed x, because that's a simpler or a quicker way to write it. We'll still use this notation over here. That actually breaks down to the basic function y equals u cubed. So what we're going to do is we're going to use substitution to differentiate or find the derivative of several of these things that look a little more complicated but can be made simpler by substitution. So in this first one, what we use, instead of the f of x form, we're going to use y form. So we'll have y equals x squared plus 2x to the 10th power. And we want to think, well, what's the basic function here? The basic function here is really just something to the 10th power. So we are going to, and I'm going to write this each time, let u equal the x squared plus 2x. And I'm going to leave a blank here because we're going to need to write something else in here later, and we'll do that each time, but this first one, I want you to see why we need to write that. So what we'll do now is we'll substitute in, so we'll have y equals u to the 10th, and we're going to differentiate this. So dy equals, and this is a power, so 10u du. So this is the differential of this one, but we want it in terms of x. Our original was in terms of x, so we want to find the derivative in terms of x. So what we need to do is substitute back in. So we get dy equals 10u. Well, we notice up here that u is simply equal to x squared plus 2x, so 10 x squared plus 2x. Oops, I forgot the 9th here. I apologize. To the 9th. du, but I don't want a du, I want this in terms of dx. And so what we need to do up here, after we take or do our let u equal x squared plus 2x, we're going to go ahead for the rest of these and go ahead and find what du is right away, because we're going to need to substitute that in later. So du is 2x plus 2 dx. So we take or differentiate those two terms, and we get 2x plus 2 dx. Now we can substitute that in for du. And so this is times 2x plus 2 dx. We wanted to find f prime of x. which means we would have to divide both sides by dx to get dy dx. So we'll have dy dx, which is equal to f prime of x, equals, and we can simplify this a little bit. We actually have 2's in common here, so we'll factor out a 2, which is 10 times 2, which is 20, x squared plus 2x to the 9th, times this 2, not 2x anymore because we factored out a 2, x plus 1. And just so you realize, again, we multiplied or divided both sides by dx. So this canceled, and that's why we have this last line is dy dx. And so there's our answer with a little bit of scribbling in there. So up here, just to make note, notice what we did. We did our u substitution, figured out what u was equal to, and then for the rest of these, we're going to go ahead and find du right away because we're always going to need to substitute back in. So for this next one, for our function h of x, we notice that our main function, first I'll write this as y equals, but our main function is a cubed root function. And when we have cubed roots and we want to differentiate, a lot of times we put it to the 1/3 power. So I'll do that in a minute, but we're going to let u equal what's inside here. So x squared plus 2x, and again we're going to find du right away, and that's 2x plus 2 dx. Now we're going to substitute u into our original, and at the same time we're going to realize to the cubed root is really to the 1/3 power, because that's, we'll be able to write it as a power function. So we have really just u to the 1/3, and we're going to differentiate. And then we're going to substitute back in. So we have dy equals 1/3 u. U we can plug back in, that was x squared plus 2x, to the negative 2/3 du, and du is right here, so that's equal to 2x plus 2 dx. Dividing both sides by dx gets us dy dx, which is the derivative. So we have dy dx, which right in our original notation from the problem is really h prime of x, is equal to, and we can write this in correct form, we have 2x plus 2 in the numerator. The 3's in the denominator from the 1/3, and then this part here is in the denominator. We have x squared plus 2x to the 2/3 power. And that is our derivative using u substitution. And then we have just several more of these that we're going to do. If you want to, you could pause and work ahead and see if you can figure them out. So here we go. Once again, we're going to let this equal y. And looking at this, we notice that our main or our basic function is natural log, so we'll let u equal the part inside the natural log, so x squared minus 42. We realize that we're at some time going to need the differential of du, so that's 2x dx. And we're going to substitute. So we have y equals the natural log of u. And what natural log of u, differentiate that, that's 1 over u du. And then we want to substitute back in. So we have dy equals 1 over u, which was x squared minus 42, du, which is 2x dx. Substituting this in for there. And then we can simplify this. We can divide both sides by dx. And that's our derivative. Again, it is in the other function form, so dy dx, which is equal to g prime of x, that equals 2x over x squared minus 42. And so that's differentiating by u substitution. Our next one, notice our basic function here is really sine of something. So we will maybe skip a step here. We're going to let u equal t cubed minus 15, which means du equals 3t squared dt. And we want to find f prime of t. We're going to, again, use y equals form here to start with. So y equals sine of u. And we know the differential of sine is cosine of u du. And we want to substitute back in. So cosine of u is this t cubed minus 15. Du is right here, so that's 3t squared dt. Dividing both sides by dt gets us the derivative that we want. Cancels over here, and dy dt, which really is just equal to f prime of t, equals, I'll put the 3t squared first, 3t squared cosine of t cubed minus 15. And that is our answer. So we figure out what the main function is. It was sine here. We make our substitution for u, find du because we know we're going to need it later. Write the function with the substitution for u, putting u in, and then differentiate and start plugging things back in. This one we mentioned before, we saw it at the beginning. This is already in y form, so we don't have to do f of x or f of t and switch it back over. But remember, and you don't have to write this anytime, what this notation means is sine x cubed. So we're going to notice that this is actually a cubed function is the basic function, so we'll let u equal sine of x, which means du is cosine of x dx. We'll make our substitution. Instead of writing sine of x cubed, it's going to be just u cubed. Differentiating with the power function, bring the 3 out front. This is 3u squared du. And then substituting back in, we get dy is equal to 3, plugging sine of x back in for u, and then du is cosine of x dx. And we can write that as dy over dx, because when we do both sides by dx, equals, put the 3, and then remember we can write sine squared in this form, and then times cosine x at the end. Here's another already in y equals form. So we notice that the main function here is a cosine. We're taking the cosine of something, cosine of e to the x. So we will let u equal e to the x, which it's nice and easy to find du, e to the x dx. Now we'll make our substitution. Y equals the cosine. Instead of writing e to the x, we can just put u in. Differentiating. Differential of cosine u is actually negative sine u du. Substituting back in, we get dy negative sine of u. U was e to the x. Du is e to the x dx. Dividing both sides by dx will give us the solution that we need, or the answer that we need. So dy dx is equal to, again, I'm going to change this around. This is negative e to the x sine of e to the x. That's the differential, or the derivative of y equals cosine e to the x. Moving to the next one, we see the main function is a square root function, or really to the 1/2 power. So we will let u equal e to the x plus 1. I think that might, no, never mind. Du equals e to the x plus 0 dx. And so we can make our substitution y equals u to the 1/2. Differentiating using the power rule, we bring the 1/2 here, u to the negative 1/2 du. Substituting back in, dy is, we know we'll have a 2 in the denominator. This negative 1/2 here that we have really is a positive 1/2 in the denominator, so we move that to the denominator to the 1/2 power, and we can plug in for u. So this is e to the x plus 1, which is what our u was, to the 1/2. And then we can substitute in for du, that was just e to the x dx. And then dividing both sides by dx, or multiplying by 1 over dx by the reciprocal, we'll get dy dx. Now the form they asked for it here was y prime, so we'll just say that's equal to y prime, which is equal to e to the x over 2 times e to the x plus 1 to the 1/2 power. And that's our derivative there. Our last one, we have y equals natural log of the absolute value of cosine of x. So we will do our substitution. We notice this is actually just a natural log question, so we want, we'll let u equal cosine of x. When we differentiate, we know that that is du equals negative sine of x dx. We'll go ahead and differentiate. That is, substitute. So we have y equals the natural log of u. Now we'll differentiate. That's dy equals 1 over u du. And substituting back in, so we'll have, really our dy is in the numerator here, so in the numerator, sorry, the du is in the numerator, du is negative sine of x dx, and u was equal to cosine, so that will go in the denominator. Dividing both sides by dx gives us dy over dx equals negative sine of x over cosine of x, and we should recognize sine x over cosine x as one of our identities, one of the ones that we use often. Sine over cosine is really tangent, so our answer is negative tangent of x. And so that's the derivative of that. So that's u substitution. Hopefully you've seen enough examples to be able to make pretty good sense of that. And that's all.